Hey yo, what is going on? It's your boy. Today we're going to be continuing and branching off of proofs, and we'll be talking about proof by induction. And essentially, proof by induction allows you to prove statements about arbitrary numbers that we'll call n, or n, by proving it's going to be true when n equals 1, and assuming it's true for when n equals k, and assuming that when n equals k, it's also true for n equals k plus 1. So by proving it's going to be true, and typically k belongs to the set of all positive integers, so k belongs to the set of all positive integers. And when we assume n equals k, we show that it is also true for n equals k plus 1. So in brief, we have our first step. And this is called the basic step, where we show that p of n, your function of n, when n equals 1 is true. Your second step is what we say your assumption, and your assumption is that n equals k, where k belongs to the set of all positive integers. And then our third step is the induction step. In other words, we're showing that when we assume that n equals k, essentially n equals k plus 1 also holds true. So let's do an example. Let's use mathematical induction to prove this statement. Our first step, we said, was the basic step, so we proved that the statement holds true when n equals 1. So let's do n equals 1. Here n equals 1 is our first term, which is 3. So 3 should equal 1 to 1 plus 1. And 3 equals 3, so n equals 1 is correct. Our second step is to assume n equals k. So we assume that n equals k, where k belongs to the set of all positive integers. And so if we assume that n equals k, our statement would look like this. Now that we assume that n equals k, we need to show that n equals k plus 1 also holds true. So we rewrite the statement such that n equals k plus 1 is present in the sequence. And because it's k plus 1, we also do, we essentially also show that, again, k plus 1 is also in the sequence. So how do we do that? We replace every k we see with a k plus 1. So we see a k, we replace that with k plus 1. So one thing you might notice is like, hey, we can use the n equals k assumption to simplify this expression here. So this, in the green, simplifies to this. And we know that because we assume that n equals k. And this sequence right here makes that shortcut or substitution for us. 4k. K plus 1, 2k plus 3. After that, it's just a matter of expanding everything out. It's all a matter of kind of working this out. So this would be 2k squared. K times 1 is just k, plus 4k plus 3 is equal to 2k squared plus 3k plus 2k plus 3. This just simplifies to 5k. And in order to show that k plus 1 holds true, we have to prove that the left-hand side of the equation equals the right-hand side. And so how do we do that? Well, if we erase this and add the sums, the constants up, we get 5k. And so left-hand side equals right-hand side. So this is correct. And so that's one example. Another example, a more common example you might see in the HL syllabus is this one. We use induction to prove that. Sorry, I need to take a call. Hello? Hello? Hello there. Sorry for that interruption. I just needed to call my brother there. Another common HL topic, or I guess question in the subtopic, is using induction to prove a sequence, an arithmetic sequence. So let's write this one down. Sn equals 1/2 n, or you can write n over 2, whatever works for you, 2u1 plus n minus 1d. And so our goal here is to essentially prove this using induction. And so our first step would be assuming n equals 1. And if we assume n equals 1, that would mean that our S1 would equal U1. So by plugging in n as 1, we need to show that S1 equals U1. So let's do that. 1/2 of 1 times 2u1 plus 1 minus 1d. So 1 minus 1 is 0, 0 times d is 0, 0 times d is 0. 1/2 1 is 1/2. 1/2 times 2u1 is just 1/2 times 2u1 is just u1. So S1 equals u1. Our assumption here is correct. The next assumption we make is that n equals k for k belonging to the set of all belonging to the set of all positive integers. So let's do that. We essentially substitute n for k. So S of k equals 1/2 k plus 2u1 plus k minus 1d. After doing this assumption, we say that n equals k plus 1 and prove this to be true. So S of k plus 1 is simply equal to S of k, or S of k, plus uk plus 1. S of k, as we said, we established here that S of k is equal to this expression. So 1/2 k 2u1 plus k minus 1d. U of k plus 1, we can just kind of write that down as, my friend again, as kd. Because along with the sum of k, we're adding k differences, if that makes sense. So we write k times d. After this, it kind of becomes a simplifying game. So it becomes k ku1 plus, I guess you can say this is 1/2 k minus 1, d, oops, this should be plus u1 plus kd, sorry, d plus u1 plus kd. After that, it becomes k u1 plus u1 plus k over 2, or 1/2 k, of k minus 1d plus kd. After that, we can factor out a k. So it becomes k u1 plus 1 plus kd k minus 1 over 2 plus 1. Right. After that, it becomes pretty simple. We can write the expression as k plus 1 over 2 times 2u1 plus k plus 1 minus 1 d. And if we substitute k plus 1 for n, we get the same expression we get here. And so we've proven it's correct. So I hope that video makes a bit more sense and it clears things up you had about proof by induction, and hopefully moving forward you can have a bit more leeway working with problems like these.